we are looking at the derivative of some inverse trigonometric functions. So, first one we're going to look at, derive, is the derivative of the inverse sine of x. Here's how I'd like you to do it. We're going to let y equal the inverse sine of x. If you recall, the domain is from -1 to 1, and we need to find. So if y equals the inverse sine of x, we want to find dy dx for that scenario. So once we have y equals the inverse sine of x, we're going to rewrite this using the definition of inverses to be x equals the sine of y. At this point, we're going to draw a right triangle representation of that. So this is telling me that the angle is y and that the sine of y is equal to x, or x over 1. So we know the sine is opposite over hypotenuse. So the sine of the angle y is in fact x over 1. At this time, it is also appropriate to find the missing side, which would be the square root of 1 minus x squared. I do in fact want you to draw that right triangle. Now that I have x equals sine y, it is simply a matter of doing implicit differentiation. So the derivative of x with respect to x is 1, and the derivative of sine y with respect to x is cosine y times dy dx. And as we stated before, the goal is to find dy dx, which would be 1 over the cosine of y. And that's going to be 1 over, and then the cosine of y is the square root of 1 minus x squared. Isn't that beautiful? And that's it. That's what dy dx is. Now you will notice from a mathematical perspective, before we looked at it graphically, but from a mathematical perspective, the only values of x that are permitted in this expression are -1 to 1, not including the -1 and 1. And that validates our graphical analysis that dy dx has that domain, and also on that domain, dy dx is always positive. Isn't that nice? So I'm going to come over here and write my final answer, 1 over the square root of 1 minus x squared, and I am going to write the domain of that. This gets added to our book of memories. All right, let's move on now to the next one. And the next one, we're going to develop the derivative with respect to x of the inverse tangent of x. What I think you should do at this point is press pause and see if you can't develop this on your own, because that's what I would do if you were in class. Okay, here I go. I'm going to start off with let y equal the inverse tangent of x, which has -infinity to infinity as its domain, and the goal is to find dy dx under the way I defined it. So I start off by saying that x is the tangent of y. That leads me to draw the right triangle representation. There's my angle y. And the tangent of this angle y is x over 1, as I have just corrected here. The tangent is opposite over adjacent, x over 1, which leads the corresponding missing side to be 1 plus x squared, radical 1 plus x squared. Now we do our implicit differentiation. So 1 equals the secant squared of y times dy dx, and dy dx will equal 1 over the secant squared of y. Or we can say equal to the cosine squared of y. So I go back to my triangle to figure out what is the cosine, which is 1 over the square root, but then that has to be squared. That final result, 1 over 1 plus x squared, is the derivative of the inverse tangent of x. I also want to look at the domain of this mathematically, and you can see that I can plug any value of x into this, and so my domain is all reals, and no matter what value of x I plug into that, this expression will always be positive, which is what we saw from the graph in the introduction. So that's kind of nice. So this equals 1 over 1 plus x squared, and that's true for all x. Now let's move on to the derivative of the inverse secant of x. Again, I think you could press pause and continue here. We're going to let y equal the inverse secant of x with the domain negative infinity to 1, union 1 to infinity, and the goal is to find dy dx as we have defined it. First, x equals x equals the secant of y, triangle, angle y. So the secant of y is x, so that becomes x, that becomes 1. And the missing side here is the square root of x squared minus 1. That's what we use later. We do our implicit. 1 equals secant of y, tangent of y, dy dx. So dy dx, the thing we're trying to find, equals 1 over secant y, tangent y. Or we could say the cosine of y times the cotangent of y. And let's look at what that equals. So the cosine of this angle here, y, the cosine is going to be 1 over x. And the cotangent is going to be 1 over the square root of x squared minus 1. And mathematically, what is the domain of this? All right, we'll work that out. And wait a minute here, something's fishy. According to our graph, the slope, with the exception of at -1 and 1, and my goodness, I made this mistake again, that's -1. But with the exception of at -1 and 1, the slope should always be positive. We've got a slight problem here. In this expression, there are values of x that we are permitted to plug into that will yield a non-positive result. So, what do you need to do to this expression to ensure that the expression's value is always positive for the values of x? Let's write the domain here. The domain of this is negative infinity to -1 and union with 1 to infinity. So that's the domain. So what do we need to do to allow, let's say, if I plugged a -2 in, that the result would be positive? If you're saying make this absolute value, then you are correct. So the secant one is one that needed a little bit of an adjustment. So the derivative is 1 over the absolute value of x times the square root of x squared minus 1. And that's going to be true on the domain. What happens if I plug in this 1? Well, if I plug in that 1, I'd be dividing by 0. That would go to infinity, and that's consistent with our graph. To summarize, I've written the derivative of 3 of the inverse trigonometric functions' derivatives, and you might think to yourself, why has he not drawn out or written the derivatives of the other trigonometric ones? Well, the reason is as follows. We have some properties here that the inverse cosine of x is simply a translation pi over 2 minus the inverse sine of x. The same is true that the inverse cotangent is pi over 2 minus the inverse tangent. And finally, the inverse cosecant is pi over 2 minus the inverse secant. So, if I wanted to find the derivative with respect to x of, let's say, the inverse cosine of x, then that would be equal to the derivative with respect to x of pi over 2 minus the inverse sine of x. This would go to 0, the derivative of a constant 0, and this would be negative the derivative of the inverse sine. So all we need to do is commit these 3 to memory, then the others are simply the negative of that. So you could see from this that the derivative with respect to x of the inverse cosecant is going to be negative 1 over absolute value square root x squared minus 1, like we see here. The absolute value ensures that the expression is always positive, but then the negative ensures that the answer is actually always negative.